Good morning to everyone. Welcome to the fourth day of FDP. Today we are going to deal about simulation of BLDC motor. Myself here is Sendilnathan, Associate Professor from EEE Department. Ajanta. We people are going to deal about basic operation of BLDC motor. Basic working principle of BLDC motor. The next one is we will have a conventional BLDC motor controller. The next one is we will deal about outgoing current hysteresis controller for BLDC motor. The last one is we are going to compare these two, that is conventional versus outgoing current hysteresis controller for BLDC motor. The first and foremost is how a BLDC motor works. It comes under special machines. This is because for the operation of BLDC motor, we need power devices. For its normal operation itself, you need power devices. Let us go into the working principle of a BLDC motor. A BLDC motor will have a stator and rotor. Let us consider we have permanent magnet rotor here. So, permanent magnets will be embedded in the rotor. Okay, and your stator is energized by three-phase supply, RYB. The phase sequence of the three phases RYB. Let us consider we have R phase here, Y phase, B phase, R, Y, and you have B phase. In BLDC motor, we are using electronic commutation rather than mechanical commutation. For mechanical commutation, we need two things. One is you need commutator and you need brush. This is not available or this is not used in our BLDC motor. Okay. What's the purpose of using a commutator? The commutator is used to reverse current. Current will be reversed. And you will have spark if commutation is not proper. Okay, let us consider the same stator here. This is our stator. Okay, this is your R phase. This is your Y phase. This is your B phase. Again R dash, Y dash, and B dash. So, if I have my rotor like this, okay, let us consider this is your rotor. Okay, what we have to do is we have to fire this R dash to make rotation. If the rotor is in this position, what you have to do is you have to fire Y dash to make rotation. And if it is in your rotor is placing near B, you have to fire B dash to make the rotor to rotate. So, the position of the rotor is more important for a BLDC motor. So, what happens here is you have a BLDC motor. This is your BLDC motor, and the position of the BLDC motor should be sensed. Position sensor is required, and this position sensor you will use only Hall sensor. Okay, and this Hall sensor is used to fire your inverter circuit, firing pulse, gate, firing pulse for inverter circuit. So you have your inverter here, you have R phase, Y phase, B phase, and the input here is DC in nature. So what we will do, firing pulses given here. So it's automatically it's a closed loop system here, and we will deal about how a conventional BLDC motor works. For this, what are the things required? You need a Hall sensor, and this sensor will be used to fire your inverter. Okay, so let us go for the conventional one. So in a conventional BLDC controller, okay, you need a DC supply. Okay, the next one is you need a inverter, and this is your BLDC motor. Okay, and from the BLDC motor, what I am going to do, I am going to sense the Hall sensor signals. For that, we have Hall sensor here. This is your Hall sensor. Okay, and this Hall sensor signals are converted into EMF. These are converted into EMF, and here gate pulses are created. Here gate pulses are created. To have a minimum control, I am using a PI controller here. Okay, let us stimulate this one. Let us take a fresh module, open. Hare Baba. File, new. Let us take a fresh module. The first and foremost, we are going to take BLDC motor. Sin power hi kaano. Okay, SIM cap, SIM power. Go to the machines and take your permanent magnet synchronous motor. Add to. The next one, what I am going to do is, let us go to the source. Go to the source. Add controlled voltage source. What are things we added? We added source here. It is controlled voltage source. We have our permanent magnet synchronous motor. And the next one is we need inverter. You can type universal inverter. Sorry, universal bridge. Let us add to the untitled one. So we got three things here. One is your voltage source. The next one is universal bridge. The next one is permanent magnet synchronous motor. Click your permanent magnet synchronous motor. Instead of back EMF waveform, you have to select trapezoidal back EMF waveform here. Don't select sinusoidal. If you select sinusoidal, it becomes PMSM motor. You have to select trapezoidal EMF waveform. That's it. So we have taken only three blocks here. One is voltage source. The next one is universal bridge. The next one is permanent magnet synchronous motor. In permanent magnet synchronous motor, your back EMF should be a trapezoidal one to make it as a BLDC motor. Rotate your universal bridge and connect your voltage source to the universal bridge. What we did, we are taken a voltage source here, a universal bridge here, permanent magnet synchronous machine, and now it is not called as PMSM. This is because you are converted your back EMF as trapezoidal, so it becomes a BLDC motor. The next one is connect your 3-phase of your universal bridge to BLDC motor. Connect your so this is so called as BLDC. Connect a universal bridge ABC that is supplied to a BLDC motor. So let us take bus selector. You have bus selector here. Connect it to your motor. You have 2 signals here. Delete the 2 signals which are selected and take your Hall sensor. Keep it in this order: Hall sensor A, Hall sensor B, Hall sensor C, and make it as a single bus. Make it as a single bus. You have to tick this output as bus, apply and give OP. So you got a single bus here. So you got your Hall sensor here. So let us deal about what happens in a Hall sensor. So we have Hall sensor here. So obviously we have 3 Hall sensor: HA, HB, HC. So what's the purpose of using Hall sensor? That can be able to locate the position of your rotor. Okay, let us consider if your rotor is in this position, Hall sensor A will be activated. If your rotor is in this position, Hall sensor B will be activated. And if a rotor in this position, Hall sensor C will be activated. So obviously we have 3 Hall sensor. It will produce zeros and ones depending upon the position of your rotor. So you have 3 Hall sensor here: HA, HB, HC, that will produce 0, 0, 0 at a max 1, 1, 1. Okay, so you have 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And here 2 stages are impossible in nature. This is because it is impossible for a rotor to be at Hall sensor 1, 2 and 3. So this state is impossible. And we have another state also, 0, 0, 0. This is also not impossible. This is because your rotor is not captured by Hall sensor A, B as well as C. So we have only 6 active stages here. Okay, we got 6 active stages here. So 0, 0, 0, it is inactive, and 1, 1, 1, it is also inactive. So we got only 6 stages here. Stage number 1 is 0, 0, 1. Stage number 2 is 0, 1, 0. And when HC becomes 1, HC becomes 1, your EMF is generated in 2 windings. One is B phase winding and C phase winding. C phase got positive pulse and B phase got negative pulse. Okay, so what we have to do? After writing your Hall sensor, EMF will be created. Let us consider we have your rotor like this. So what happens? EMF will be created in R phase, okay, and if it is in between R and Y, EMF will be created in R phase as well as in Y phase, okay, and one will be positive, another will be negative. So copy this one. my first aim is to create this EMF. Okay, we are supposed to create this EMF. How to create this EMF? We got our Hall sensor. யாராச்சும் காப்பி பண்றீங்களாமா? Yeah. From this, at any stage, only two phases are energized. Okay, one in positive, another one in negative. How to find your EMF? Let us consider we have HA, HB, HC. Okay, and what I am going to do is HA is compared with HB dash, HB is compared with HC dash, HC is compared with HA dash. Okay, what I am going to do, I am using an AND gate here, where the input of the AND gate is HA, HB dash, HB, HC dash, HC, HA dash, and in the next sector we will have HA dash, HB, HB dash, HC, HC dash, HA. So we got 1, 2, 3, 4, 5, 6, and convert this one. This is because it is in Boolean. Convert this one. Using a adder or summer, 1, 2, 3, and this is 1 dash, 2 dash, 3 dash. 1 and 1 dash will give you EA, and 2 dash will provide EB signal to us. 3A will give me EC signal. Okay, what you have to do, you have your so-called as Hall sensor. Okay, what you are going to do, you are going to compare your Hall sensor, individual Hall sensor as in this table, and we will create EA, EB and EC. So what we have to do, so we got our Hall sensor here, and this Hall sensor consists of 3 input. What are they? HA, HB, HC. Okay, so let us take, go to logic, logical, take AND gate, and mux, So the top one gives me HA, HB, HC. The bottom one gives me HA bar, HB bar, HC bar. What we have to do? Let us take a AND gate here. How many AND gates are required? We need 6 AND gate. AND gate. First AND gate, HA, HB bar should be taken. Second AND gate, for second AND gate, HB, HC bar. For third AND gate, HC, HA bar. Okay, let us go for the next sector. HA bar, where is HA bar? It is here. HB, next one, HB bar, HC. Next one, HC bar, HA. Okay. Now you need a converter. Convert. Convert enga irukuna, it's in logic bits. You don't have logic bits common.
Data type conversion sir. Adana convert. Ade data type conversion.
Mela. Yeah. Don't do anything in this. Just connect your converter to AND gate. First one. Second, 2 second. Third to third. From the hall sensor, we implemented a circuit which converts hall sensor signal to EMF. Okay, so we got EA, EB, EC here. The next one, this EMF should be converted to gate pulse. How to do that one? So we have the next one, the back EMF should be converted into, this should be converted into back EMF EA, EB, EC, that should be converted into gate pulse. So if you have -1 for B and +1 for C, gate pulse should be given for 4th and 5th switches. So we have our inverter switches here. Let us go for the inverter. So you have an inverter switch where inverter is powered by means of DC supply and output is AC in nature. Okay, and your output is AC in nature, A, B, C. Okay, so what we have to do is we have positive switches here and negative switches here. Okay, 1, 3, 5, 6, 4, 2. 2, 6, 4. Okay, so what happens here is 4 and 5 are fired. When 4 and 5 are fired, what happens here is your network will be closed like this. 5 in the top edge and 4 in bottom edge is closed. So 5 is connected to C and 4 is connected to A. So A and C will be energized. And how to do this one? It is very easy. What you have to do is compare this one compare to 0, type compare to 0, you will get a compare to 0 here. Change the operator to greater than equal to. Next one to less than equal to. Take a mux in which this mux need 6 input. Yeah, so this is a mux which has 6 input connected in order. and this should be given to firing pulse. That's it. Where is our firing pulse? It is here. Yeah. Okay. What we did? We have Hall sensor. From the Hall sensor, EMF is created here. EMF EA, EB, EC is created here. From EA, EB, EC, gate pulses are created here. This is gate pulse 1, this is gate pulse 6, and it is connected to the firing pulse here. For the inverter gate pulse, it is connected. Okay, the next one is, let us go to let us give reference speed here. Let us go for the common used block. Type constant. Let us give input as 1000, 2000. So this is your input, and it should be compared with our reference signal. So you don't have speed here. For that, take this bus selector, connect it with your motor, discard your Hall sensors. Let us take speed. The next one is torque. So I am going to take two things here. One is speed, another one is torque. And don't select this output as bus. If you select this output as bus, it will convert as a single output. So you got two output here. The first output is speed. The first output is speed. The second output is your torque. Okay, and the speed. This is in radians per second. To convert this one, let us take the gain one. Gain. In gain, you are supposed to provide 30 divided by pi. Pi should be in small letter. Apply, okay. So this is our actual speed. This is our reference speed. Okay, this is our reference speed. This is my reference speed. And it is compared with the actual speed. So you need a comparator. Point 0110. PID, let us take PI controller here, where the P value is 0.01 and the integral value is 10. Rotate, and you need a summer, no? Sum Okay, positive should be the reference speed and negative is your actual speed. And it is given to the PI controller, and this is fed as the controller for your controlled voltage source. So what I did is, I taken the speed, converted the speed to RPM using 30 divided by pi, and it is compared with the reference speed. You will get the error. Error is given to the PI controller. In PI controller, proportional one is gain constant is 0.001. Integral is taken as 10, and it is given as the என்னடா இப்படி போகுது. Okay, the last one is we have to take power guy. Okay, so let us make the reference torque as constant. Let us make the reference torque as 5. So we provided reference speed as 2000 and reference torque as 5. So what are the things we have to capture in the scope? One is speed, the next one is torque. Speed, the next one is torque. Arey Baba. Let us run the simulation. Okay. என்ன ரிவர்ஸ்ல போகுது? இது தப்பு பண்ணியிருக்கேன். Oh, amplitude. Provide 200 as amplitude. Voltage source, provide 200 as amplitude. என்ன இது? UID தானே போட்டிருக்கேன். Greater than 0, less than 0, greater than 0, less than 0, greater than 0, less than 0. Here. Untitled. 0.01 10 universal first one ma'am சரிங்க மேடம் let us have a break.